You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. In this video, we will look at seabed friction. OrcaFlex includes a simple friction model which can give an approximate representation of contact friction with the seabed, as well as contact friction between lines and elastic solid shapes, lines and supports, and lines with other lines. It is also possible to model friction between buoys and elastic solid shapes, as well as buoys and the seabed. However, this video will focus only on friction between lines and the seabed. This simple friction model is suitable for many global analyses that might be performed in OrcaFlex. Some analyses may require more detailed modelling of seabed interaction, for example, modelling the accumulation of soil in front of a line as it moves laterally. Some of these types of effects can be captured using a tangential resistance profile, which we can specify on the seabed page of the line data form. I will come back to this option later. We need to remember, however, that OrcaFlex is a global analysis tool and the capturing of very detailed seabed interaction is beyond its scope. OrcaFlex by default utilises a modified Coulomb friction model, details of which can be found in the help file, here, in the theory section, under friction theory. Friction is a dynamic phenomenon, so the question arises as to how we deal with friction when working with a static analysis. Let's take a look at this with a model based on the riser system we have built in previous videos. The table on screen shows us the data used to create this model, but if you have saved the buoyancy attachments example from video 10, you can use this as a basis. Otherwise, pause the video now and build a new model using the data in the table. If you need further guidance in building this model, refer back to video 10, which is entitled Adding Line Attachments. The previous model is elaborated on by the inclusion of an additional line representing one of the moorings. This line needs to represent a chain, and as such, its line type can be created using the line type wizard. To create the chain line type, open the line type data form and add a new line type called chain. With the new line type selected, open the line type wizard at the top right corner of the data form. Ensure the chain category is selected and click Next. On this page, input a bar diameter of 0.08 meters and the stud link type. Once this has been done, close the wizard, and on the drawing page, change the pen color for the chain to be blue. Then close the line type data form and add a new line to the model with the following properties. The line is called mooring 1, and its length is 350 meters, with end A connected to the vessel at a position of 35, -1, and -7. End B will be anchored with a height above seabed of 0. We also need to make sure we specify the new chain line type we have just created. At this point, everything is set for this new line except for the position of the anchored end. Sometimes we know a Cartesian coordinate position for a line end, but we may also have this information in the form of polar coordinates, a radius and heading, as is the case here. There is no means of entering polar coordinates on the line data form, but we can do this via the All Objects data form. This data form allows you to view and edit the data for all the objects in a model in one place, and includes the ability to set polar coordinates for end connections. Select the option to show Connections, and then go to the Polar Coordinates page. And here we can set the mooring end B position to be 300 meter radius and -30° theta relative to end A. This example could use either the global coordinate system or the vessel as reference axes, since the vessel is currently on a 0 heading. However, this will not always be the case, so the choice should be made here based on what reference axes the provided data is relative to. If we look at the side elevation and run statics, everything seems to solve as expected. However, moving to the plan view reveals an issue with the solved state of the mooring line, with it forming a curve rather than the expected straight line from the anchor point back to the vessel hang-off. This shape is a result of an assumption that needs to be made by the program. In dynamics, OrcaFlex has a history of motion, but there is no history in statics unless dealing with a restart analysis. We therefore need to tell the program how the line was originally laid, so that when we want to consider seabed friction, those friction forces can be applied in the correct direction. We do this by specifying a lay azimuth value, and optionally an as-laid tension. We can see the lay azimuth value is set at 180 degrees by default, and unless we change this, OrcaFlex will lay the line from the anchor point along this heading, which is horizontally from right to left as we look at the screen. Remember that in OrcaFlex, 0 degrees is in the positive x direction. In order for the line to be laid in the direction we expect, we need to know the heading of the anchor point relative to the top end of the line. In this case, we know the line had a heading of 30 degrees from horizontal when viewed in plan, which would translate to a lay azimuth value of 150 degrees when working back from the anchor point. This isn't always easy to work out, so we have an option to set this automatically by right-clicking on the lay azimuth value and selecting Set Lay Azimuth. This measures the direction of a line drawn from the anchor point back to the top end when looking in the plan view, and sets the value accordingly. Now, when we run statics, we see the line solve as expected. Note that the Set Lay Azimuth heading depends on the reset position of the line ends, so these need to be set appropriately. There is an exception to the need to specify a lay azimuth, and that is if the Step 1 statics method is prescribed, in which case the originally laid position is taken to be that defined by a prescribed track. When this method is selected, a new page becomes visible, prescribed starting shape, allowing us to draw this track on the seabed, and towards which frictional forces will act. I will save this file now, as we'll come back to it in a moment. But before we do, I want to come back to some enhancements and alternatives to the standard Coulomb friction model. Firstly, it is possible to decouple lateral and axial friction, which doesn't average the lateral and axial friction coefficients, instead treating them as independent forces. Secondly, it is possible to allow seabed contact forces to be applied at the line's centre line, when torsion is included, rather than at the point of contact. Without this option, you may see some line twisting as a result of seabed contact, which could be unrealistic in certain scenarios, such as if the line was embedded in the seabed. This is demonstrated in this example, currently twisting as it moves along while embedded in the seabed. If we reset it, then select the option to apply contact forces at the centre line, the line no longer twists in the resultant replay. Next, as well as being determined by the seabed friction coefficient and modelled by Coulomb friction, the tangential resistance can also be defined as a resistance versus displacement curve in either or both the lateral and axial directions. This will be useful for applications such as pipeline breakout or slip. These resistance profile models can be used instead of or in conjunction with the Coulomb friction model. This particular case is an example with a simple trilinear displacement resistance profile. The seabed page of the line data form shows a variable profile for lateral resistance, and if we look at the data, we see that the resistance increases linearly for the first 4 meters, before decreasing linearly for the next 2 meters, and then remaining constant. This could be a simplified representation of a line being pulled through or over a berm where the resistance is initially higher until breakout occurs. The motion of the line here is being driven by an imposed motion constraint, where displacement in y is equal to time. And we can infer the tangential resistance by looking at a plot of the constraint connection force. You can see that the use of the trilinear resistance profile has resulted in a trilinear constraint connection force, even though the displacement is linear. This is one simple example of using a tangential resistance profile. For more information, including a look at some more complex examples, take a look at the video from the OrcaFlex 11.2 user group meetings. Just look for the OrcaFlex 11.2 new features video in the What's New section of our videos page. Coming back to the file we just built, we now need to introduce an additional mooring line, which we can use to demonstrate some useful features of the model browser. We could obviously just introduce a new line and then enter the required properties, such as its length and line type used. However, we are creating a new line which is very similar to the existing mooring. So it will be quicker to just duplicate this line. This is as simple as highlighting it in the model browser and using the Windows copy-paste commands, either from the context menu or using the usual keyboard shortcuts. This places a copy of the line in the model and automatically increases the numerical suffix by 1. We now have 2 identical lines in the same position. Again, we could manually enter the end positions for the new line to reposition it as required, but we can use another model browser feature to move the new line. Highlight the new line, Mooring 2, right-click and select Move Selected Objects, which opens a wizard for moving the selected objects. This could be one or more objects. We can choose one or both ends of the line, and we can move by a number of methods shown here. In this case, the new mooring can be moved by rotation, which requires an angle and centre of rotation. The current position is 30 degrees below the global x-axis when viewed in plan. The new position needs to be 30 degrees above the global x-axis when viewed in plan, so a total rotation angle of 60 degrees. For the centre of rotation, zooming in on end A of the line shows that we need to extrapolate it back to the centre line. And some simple calculations will tell us that this point is an x value of 33.27 and obviously a y value of 0. Having entered the data and clicked Move, we see the line moved as intended. Note that the rotation is only in the horizontal plane. We also see the lay azimuth of the new line has been automatically updated when using the Move Selected Objects wizard. This would not have happened if we manually positioned the line. While we're discussing model browser tools, it's worth pointing out some other useful tools here. First of all, the ability to locate an object, useful if you have multiple similar objects in a model. Select the object and use the Locate option in the context menu, or the F3 shortcut. This will either flash the object in the 3D view or temporarily hide all other objects. Next, we can lock objects to avoid them being accidentally dragged or connected in the 3D view. I can drag a line end currently, but if I lock the lines, it's no longer possible to drag the line end. We can select and compare two objects from the context menu to look at the differences between them. In this case, if we select the two mooring lines and press F8, this opens up a comparison tool with the differences in the two lines highlighted. For these mooring lines, that includes the names, the connection positions, and the lay azimuth values. We can, with View by Groups selected, group objects into folders in the model browser. To do this, we just need to add a group. We can then name this group. We can then drag objects into it. Next, we have the ability to hide selected objects with the Ctrl-H shortcut. The same shortcut will subsequently show an object that's been hidden. This can be applied to a single object, multiple objects, or even a group of objects. Note that they are still active in the model, just not visible. We can also select a group or multiple objects and look at their compound properties from the context menu. This is the usual way of accessing properties in OrcaFlex with the Alt and Enter shortcut. For a group, this will provide some useful additional information such as centers of mass and volume for the group. Final model browser tool to discuss is the library. A library is a collection of OrcaFlex objects stored in an OrcaFlex data file. This is a good way to store commonly used data, for example, line types for standard cables or risers that are repeatedly analysed, or vessel objects representing the ships in a company's fleet. When you're creating a new model which can make use of an object in one of your library files, you can access it from the context menu of the model browser, as can be seen here. Select Open, or select the library file from the Recent Files list. This opens a second model browser from which you can select one or more objects or object types, and then copy these across to the new model with the Import button. Once you have finished, simply close the library file again from the context menu. That was a summary of seabed friction, as well as some additional features in the model browser. Our next video will focus on the buoy objects.